Hello there, and welcome to the Sleepless Scientist. Tonight, we're journeying to a place no human has ever been, and likely never will go, the center of our planet. Beneath your feet right now, through layers of rock and metal, past temperatures that would vaporize steel, and pressures that would crush submarines like tin cans, lies Earth's core. It's a realm of liquid iron spinning in darkness, generating the invisible shield that protects all life above. We know about this hidden world not by visiting it, but through echoes seismic waves from earthquakes that ring through our planet like a bell, revealing secrets in their reverberations. As you settle in tonight, let your mind descend through the familiar crust, past the flowing mantle, and into the metallic heart that's been beating since our planet's violent birth over 4 billion years ago. This is a story of discovery, without direct observation, of understanding through ingenuity, of the mysterious engine room that makes Earth habitable. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. What lies beneath our feet? Think about the ground you're standing on right now. Solid, dependable, utterly familiar. But that surface is just the thinnest skin on something far stranger. Beneath the soil and bedrock lies a world of extreme heat and pressure, where rocks flow like honey over millions of years, and metals swirl in vast underground oceans. The earth beneath us isn't the cold, dead sphere we might imagine. It's dynamic, churning, alive with motion and energy. Every volcano, every earthquake, every magnetic compass pointing north tells us that something powerful is happening deep below. The deeper you go, the more alien it becomes. A few miles down, temperatures rise past the boiling point of water. Hundreds of miles down, solid rock behaves like putty. And at the very center, nearly 4,000 miles beneath the surface, lies a ball of iron and nickel, as hot as the surface of the sun. This core is the engine of our planet, the reason we have continents that drift, mountains that rise, and a magnetic field that shields us from cosmic radiation. Everything we see on the surface, the landscapes, the oceans, the very air we breathe, exists because of what lies hidden in the depths. The story of Earth's core is the story of our planet's heart, beating in darkness, unseen but essential. How deep does the Earth really go? Let's consider the journey to the center. If you could somehow drill straight down through the Earth, you'd travel roughly 6,371 kilometers, or about 3,959 miles. To put that in perspective, if you drove continuously at highway speed, it would take you more than 2.5 days to reach the center. Mount Everest, Earth's highest peak, rises just under 9 kilometers above sea level. The deepest point in the ocean, the Challenger Deep, lies about 11 kilometers below the surface. Both of these, the highest and the lowest points we can physically reach, are mere scratches on the surface compared to the distance to Earth's core. The deepest hole humans have ever drilled, the Kola superdeep borehole in Russia, reached only 12 kilometers before the drill bits began melting from heat. That's barely a fraction of 1% of the way to the center. The Earth is vastly deeper than our everyday experience suggests. When we think of our planet, we tend to picture the surface, the lands and seas we know. But that surface is just a paper-thin wrapper around a massive sphere of increasingly dense material. The journey inward is a journey through layers, each with its own character, composition, and behavior. And at the very heart of this nested structure lies the core, the most extreme environment in our planet, unreachable yet fundamental to everything we know. What exactly is the Earth's core? Here's something to wrap your mind around. The core isn't a single uniform sphere. It's actually two distinct regions nested within each other. The outer core is a shell of liquid metal, primarily iron mixed with nickel, extending from about 2,900 kilometers below the surface, down to roughly 5,150 kilometers deep. This liquid layer is in constant motion, churning and flowing like a vast underground ocean of molten metal. Then, At the very center sits the inner core, a solid ball of iron and nickel, about 1,220 kilometers in radius, roughly 3/4 the size of our moon. Despite being hotter than the outer core, this inner sphere is solid because the pressure is so immense that atoms are squeezed into a rigid crystalline structure. These two cores work together as Earth's engine room. The liquid outer core flows around the solid inner core, driven by heat escaping from the center and by the cooling of the planet over billions of years. This motion generates electrical currents in the conducting metal, which in turn creates Earth's magnetic field through a process called the geodynamo. The inner core, meanwhile, grows slowly as the planet cools, with iron crystallizing out of the liquid outer core and adding to the solid center at a rate of about a millimeter per year. Together, these two cores represent about 1/6 of Earth's total volume, but contain roughly 1/3 of its mass, a concentration of heavy metals at the planet's heart. How did we discover it exists? Let's go back to the early 20th century, when scientists first began to peer into Earth's interior. They couldn't dig there or send probes, but they had earthquakes, nature's own seismic experiments. In 1906, British geologist Richard Dixon Oldham was studying records from seismographs around the world when he noticed something peculiar. When a major earthquake struck, the shaking waves didn't travel in simple, predictable paths. Some waves arrived where expected, but others created strange shadow zones on the opposite side of the planet, where certain types of waves never appeared. Oldham realized that these shadow zones meant the waves had encountered something different deep inside the Earth, something that blocked or bent them. He concluded that Earth must have a core made of different material than the surrounding rock. Later, in 1936, Danish seismologist Inge Lehmann discovered that within this core, there must be an even denser inner core, based on faint seismic echoes that bounced off an internal boundary. These scientists never saw the core, never sent anything down to touch it, yet through careful analysis of earthquake waves, reading the planet's vibrations like a doctor reads a heartbeat, they discovered the hidden structure at Earth's center. It was detective work on a planetary scale, piecing together a picture of the invisible from indirect clues, proving that we could know what we could never see. Can we ever reach the core? Think about what it would take to actually travel to the core. The obstacles aren't just difficult. They're essentially insurmountable with any technology we can conceive. The distance alone is daunting, but that's the least of the problems. The real barriers are heat and pressure. Just 10 kilometers down, temperatures reach around 200 degrees Celsius, hot enough to melt many materials. Drilling equipment starts to fail. Electronics malfunction. By 30 kilometers, still within the thin crust, temperatures exceed 500 degrees Celsius, and pressures begin crushing even the strongest materials. The deepest we've ever drilled ended at 12 kilometers, where the rock itself became so hot and plastic that it would flow into any hole we made, filling it back in faster than we could drill. Now imagine trying to go 2,000 kilometers to reach the outer core, where you'd face molten iron at 4,000 degrees Celsius and pressures over 1,000,000 times atmospheric pressure. No material we know can withstand these conditions. Any vessel would melt or crush instantly. The energy required would be astronomical. The technological challenges beyond anything we've solved. The core isn't just deep. It's inaccessible in a fundamental way. We are creatures built for the surface, adapted to a narrow range of temperatures and pressures, and the planet's interior is simply too extreme for us to physically explore. We'll know the core only through remote sensing, through the echoes and signals it sends to the surface, never through direct contact. Why can't we drill that deep? Here's the reality of deep drilling. The Kola Super Deep Borehole, begun in 1970 and abandoned in 1992, was humanity's deepest attempt to penetrate Earth's crust. After 22 years of work, it reached 12 kilometers, about 7.5 miles. To put that in perspective, that's less than 0.2% of the distance to the core. Why did they stop? The temperature at the bottom reached 180 degrees Celsius, far hotter than predicted. The drill bits melted. The rock at that depth was plastic, almost fluid, squeezing in on the borehole. Keeping it open required constant maintenance. The deeper you drill, the worse these problems become. Temperature increases roughly 25 degrees Celsius per kilometer in the crust, which means by 100 kilometers deep, still far from the core, temperatures would exceed 2,500 degrees Celsius. The rock would be flowing, the pressure immense. But the real problem is that drilling technology depends on the rock being solid enough to hold the shape of the hole. In the deep earth, rock flows over geological time. Any hole would eventually close, even if we somehow solved the material problems, created drill bits that could withstand the heat, developed cooling systems that could function at such depths. We'd be fighting against the planet itself, which would constantly try to fill in any cavity we created. The Earth is not static, but dynamic, and its interior is in slow but constant motion. We simply cannot maintain a stable pathway through it. How do we know what's inside the Earth? Let's consider the ingenious methods scientists use to study what they cannot see. The primary tool is seismology, the study of how earthquake waves travel through the planet. When an earthquake occurs anywhere in the world, it sends several types of waves radiating through the Earth. Primary waves, or P waves, are compression waves that can travel through any material, solid or liquid. Secondary waves, or S waves, are shear waves that only travel through solids. By placing seismometers around the globe and measuring when and how these waves arrive, scientists can map Earth's interior, like a CT scan reveals the inside of a human body. Waves travel at different speeds, through different materials. They bend and reflect at boundaries between layers. S waves disappear entirely when they hit the liquid outer core, creating a shadow zone that proves the core's liquid nature. P waves slow down and bend when entering the core, revealing its density. Subtle variations in wave travel times show the inner core's crystal structure and rotation. But seismology isn't the only tool. Scientists also study Earth's magnetic field, which originates in the core, learning about core dynamics from how the field changes over time. Laboratory experiments recreate core pressures using diamond anvil cells, revealing how iron behaves under extreme conditions. Computer simulations model core convection and magnetic field generation. Meteorites provide samples of iron-nickel alloys, similar to Earth's core. Each method gives a piece of the puzzle, and together they build a remarkably detailed picture of a place no human will ever visit. What are the four main layers of Earth? Think of the Earth as a nested structure, like a Russian doll, each layer with its own character. The outermost layer is the crust, the thin, brittle skin where we live. It ranges from just 5 kilometers thick under the oceans to 70 kilometers beneath mountain ranges. The crust is made of relatively light rocks, granite and basalt, rich in silicon, aluminum, and oxygen. Despite being the most familiar layer to us, it's the thinnest, accounting for less than 1% of Earth's volume. Beneath the crust lies the mantle, a vast layer extending down to 2,900 kilometers. The mantle is solid rock, but it's hot enough to flow slowly over millions of years, like extremely thick honey. It's made of denser silicate minerals, rich in iron and magnesium. The mantle contains about 84% of Earth's volume and drives plate tectonics through its slow convection currents. Then we reach the outer core, a liquid shell of iron and nickel from 2,900 to 5,150 kilometers deep. This flowing metal generates Earth's magnetic field as it churns around the innermost layer. Finally, at the very center, from 5,150 kilometers to the planet's center at 6,371 kilometers, sits the inner core, a solid ball of iron and nickel, crystallized under immense pressure. Each layer transitions into the next, boundaries marked by changes in composition, temperature, or phase. Together, They form a complex system, each layer influencing the others, creating the dynamic planet we inhabit. How thick is each layer? Let's put some numbers to this structure. The crust, where all human activity occurs, averages about 30 kilometers thick on continents and just 5 to 10 kilometers thick under the oceans. If Earth were scaled down to the size of an apple, the crust would be thinner than the apple's skin. The mantle beneath is far more substantial, extending 2,900 kilometers deep. That's nearly half of Earth's radius, making the mantle by far the largest layer by volume. The outer core, that ocean of liquid iron, forms a shell about 2,250 kilometers thick. It's a vast reservoir of molten metal, constantly in motion, swirling in complex patterns driven by heat and Earth's rotation. Finally, the inner core measures roughly 1,220 kilometers in radius, making it about 2,440 kilometers in diameter, smaller than the Moon, but incredibly dense. To visualize this, imagine Earth as a ball 12 feet across. The crust would be just a few millimeters thick, barely perceptible. The mantle would extend inward about 6 feet. The outer core would form a shell about 3 feet thick around the center. And at the very heart would sit the inner core, a solid ball about 2 feet across. These proportions reveal something important. We live on the tiniest outer shell of a much larger, mostly inaccessible structure. Everything we see, every mountain and ocean, exists on a surface that's barely there compared to the vast interior beneath. What separates the mantle from the core? Here's where things get interesting at the boundary. The division between mantle and core, about 2,900 kilometers below the surface, is one of the sharpest boundaries in Earth's interior. It's called the core-mantle boundary, or CMB, and it separates solid rock from liquid metal, silicate minerals from iron alloy. The contrast is extreme. Above the boundary, you have the lower mantle, hot, dense rock that flows slowly over geological time, but is fundamentally still stone. Below the boundary, suddenly, you have molten iron at temperatures around 4,000 degrees Celsius. The density jumps dramatically too, from about 5.5 grams per cubic centimeter in the lower mantle to about 10 grams per cubic centimeter in the outer core. This boundary isn't perfectly smooth. Seismic studies reveal irregularities, topography on the CMB, like underwater mountains, with features rising hundreds of kilometers. Some of these irregularities might be partially molten rock on the mantle side, kept liquid by heat from the core. Others might be accumulations of dense material that sank through the mantle over billions of years. The core-mantle boundary is also where intense heat transfer occurs. Heat escaping from the core drives convection in the lower mantle, creating mantle plumes that rise toward the surface, potentially feeding volcanic hotspots like Hawaii and Iceland. This boundary is a frontier between two fundamentally different realms, a place where rock meets metal, solid meets liquid, where the planet's deep heat begins its long journey toward the surface. What is the outer core made of? Think about a vast ocean of molten metal, hotter than a blast furnace, churning in absolute darkness. That's the outer core. It's primarily iron, about 85%, mixed with nickel and smaller amounts of lighter elements. Scientists know the exact composition from several lines of evidence. First, the density. Seismic waves reveal that the outer core is less dense than pure iron would be at those pressures and temperatures, which means lighter elements must be mixed in. But which elements? The candidates include sulfur, oxygen, silicon, carbon, or hydrogen, elements that could have been incorporated during Earth's formation and became trapped in the core as the planet differentiated. The exact mix is still debated, but these light elements are crucial. They lower the core's melting point, keeping it liquid. They also create compositional buoyancy. When iron crystallizes onto the inner core, it leaves the lighter elements behind in the liquid, making that liquid less dense so it rises, driving convection. This convection, powered by both heat and composition differences, is what keeps the outer core in constant motion. The liquid metal flows in complex patterns, influenced by Earth's rotation, by the magnetic field it generates, and by heat escaping from the inner core. It's not a simple, uniform layer, but a dynamic system with currents, eddies, and waves of liquid iron flowing at speeds of kilometers per year, generating the magnetic field that protects life on Earth's surface. Why is the outer core liquid? Let's explore the physics of why the outer core remains molten. Iron's melting point depends dramatically on pressure. At Earth's surface, pure iron melts at about 1,538 degrees Celsius. But as pressure increases with depth, the melting point rises too. At the pressures of the outer core, between 1.3 and 3.3 million atmospheres, iron's melting point climbs to somewhere between 4,000 and 5,000 degrees Celsius, depending on composition. The outer core sits in a Goldilocks zone, where temperatures are high enough to keep the iron liquid, but pressures aren't quite high enough to force it into a solid state. As you descend through the outer core toward the inner core, pressure steadily increases. At the boundary between them, about 5,150 kilometers deep, the pressure finally becomes high enough, about 3.3 million atmospheres, that iron crystallizes despite the increasing temperature. This boundary, called the Bullen discontinuity, marks where liquid metal transitions to solid crystal. It's not a sharp line, but likely a transition zone where solid crystals coexist with liquid metal, like a slush. The liquid state of the outer core is essential for Earth's magnetic field. If the entire core were solid, there would be no fluid motion to drive the geodynamo. If it were entirely liquid, there would be no inner core to provide the crystallization that releases latent heat and drives convection. Earth's core exists in precisely the right state to maintain both regions, creating a self-sustaining system that has protected our planet for billions of years. What is the inner core made of? Here's what lies at the very center of everything. The inner core is predominantly iron, probably between 80 and 95%, with the rest being nickel and trace amounts of other elements. But this isn't ordinary iron. Under the extraordinary conditions at Earth's center, pressures exceeding 3.6 million atmospheres and temperatures around 5,200 degrees Celsius, iron takes on a specific crystalline form called hexagonal close packed, where atoms arrange themselves in repeating hexagonal patterns. This crystal structure gives the inner core unusual properties. Seismic waves travel through it at different speeds depending on their direction, faster along Earth's north-south axis, slower in other directions. This anisotropy tells scientists that the iron crystals have a preferred alignment, possibly produced by the inner core's rotation or by the magnetic field that permeates it. Some research suggests there might even be different regions within the inner core with different crystal orientations. The inner core also likely contains light elements mixed into the iron-nickel matrix, though less than the outer core. These impurities affect its properties, its density, its melting point, how sound travels through it. The inner core is growing slowly as Earth cools, with iron crystallizing from the liquid outer core and adding to the solid center. This process releases latent heat, the energy freed when liquid becomes solid, which helps power convection in the outer core. The inner core is ancient, alien, and yet fundamental to maintaining the magnetic shield that makes life on Earth's surface possible. How solid is the inner core? Think about what solid means under such extreme conditions. The inner core is solid in the sense that it maintains its shape and doesn't flow as a liquid. Its atoms are locked into a crystalline lattice, unable to slide past each other freely. But solid doesn't mean unchanging or static. Under the immense pressure and temperature, the atoms vibrate with tremendous energy. The crystal structure itself may undergo slow deformation over geological time, Recent research has suggested the inner core might be softer than previously thought, perhaps more like gold at room temperature than like hard iron. Still solid, but somewhat malleable. The boundary between the solid inner core and liquid outer core isn't perfectly sharp. There's likely a mushy transition zone where solid iron crystals coexist with liquid metal, like a slush or a half-frozen drink. The thickness of this zone and its exact nature remain uncertain. The inner core also isn't perfectly uniform. Seismic studies reveal variations in how waves travel through different parts of it, suggesting regional differences in crystal structure or composition. Some scientists think there might even be an innermost inner core, a central region about 650 kilometers in radius, where crystals are aligned differently than in the outer part of the inner core. The inner core is solid, yes, but it's a dynamic, complex structure influenced by pressure, heat, rotation, and the magnetic field, constantly evolving on timescales too slow for us to perceive, but real nonetheless. How hot is the Earth's core? Let's contemplate the temperatures at our planet's heart. The inner core reaches approximately 5,200 degrees Celsius, or about 9,400 degrees Fahrenheit. That's extraordinarily hot. Hot enough to vaporize any material at surface pressure. How do scientists know this? They can't insert a thermometer, so they use several indirect methods. Laboratory experiments measure iron's melting point at high pressures using diamond anvil cells. Seismic wave speeds through the core are sensitive to temperature. Computer models of core dynamics match observations only with specific temperature ranges. All these methods converge on similar estimates. Where does this heat come from? Primarily two sources. First, primordial heat, the energy left over from Earth's violent formation 4.5 billion years ago, when countless rocks and planetimals smashed together, converting their kinetic energy into heat. The collisions were so energetic that the entire planet was likely molten initially. Second, radioactive decay. The core and mantle contain radioactive elements, uranium, thorium, potassium, that slowly decay over millions of years, releasing heat as they do. This radioactive heating has sustained Earth's interior temperature long after the primordial heat alone would have allowed significant cooling. The combination of these heat sources keeps the core scorching hot, maintaining the liquid outer core, driving convection, and powering the geodynamo. The heat is slowly leaking out, radiating through the mantle to the surface, and eventually into space. But the process is so gradual that the core will remain hot for billions of years more. Is it hotter than the sun's surface? Here's a comparison that captures the imagination. The surface of the sun, the photosphere we see shining in the sky, has a temperature of about 5,500 degrees Celsius. Earth's inner core, at roughly 5,200 degrees Celsius, is almost as hot. In fact, different estimates and measurements can place the core at the same temperature or even slightly hotter than the sun's surface. This seems impossible. How can our relatively small planet have a center as hot as the surface of a star? But remember, we're only comparing to the sun's surface, its coolest region. The sun's corona, its outer atmosphere, reaches millions of degrees, and its core burns at about 15 million degrees Celsius, far hotter than anything on Earth. Still, the comparison is startling. It reveals the intense violence of Earth's formation and the enormous energies still trapped in our planet's depths. The difference is in energy sources. The sun's heat comes from nuclear fusion, hydrogen atoms smashing together under gravity to form helium and release energy. Earth's core heat is thermal energy from formation plus radioactive decay, fossil heat, stored and slowly dissipating. The sun will shine for billions more years, powered by fusion. Earth's core is cooling, though slowly, losing heat to space bit by bit. But for now, for the entire span of human existence, and far into the future, our planet's heart remains as hot as the face of our star, a hidden furnace at the center of the world we know. How does the core generate heat? Think about the two engines that keep Earth's core hot. The first is primordial heat, a gift from the planet's birth. When Earth formed 4.54 billion years ago, it assembled from a disk of dust and gas orbiting the young sun. Small particles stuck together, forming larger and larger bodies. Eventually, planets the size of mountains and small moons collided at tremendous speeds, perhaps tens of kilometers per second. Each impact converted kinetic energy into heat. The larger Earth grew, the harder objects hit, and the more heat was generated. The process was so energetic that much of the early Earth was molten, a magma ocean covering the surface. The interior a churning mix of liquid rock and metal. As the planet cooled slightly, denser iron sank toward the center through the liquid rock, a process called the iron catastrophe. This released even more energy, like a massive amount of potential energy converting to heat. The iron formed the core. The lighter rock floated above to form the mantle and crust, and Earth was left incredibly hot. The second heat source is radioactive decay. Elements like uranium-238, thorium-232, and potassium-40 naturally break down over time, transforming into lighter elements and releasing energy. These radioactive elements are concentrated in the mantle and crust, but they contribute to the core's heat by warming the surrounding material. Together, primordial heat and radioactivity keep the core at temperatures that would melt mountains, drive volcanoes, and generate magnetic fields, powering our planet's geological activity billions of years after formation. Why hasn't the Earth cooled down yet? Let's consider why Earth remains geologically active after more than 4 billion years. The answer lies in size, composition, and insulation. Larger objects retain heat better than smaller ones because volume increases faster than surface area. Earth is large enough that heat generated during formation and from radioactive decay can't escape quickly. The mantle and crust act as insulating layers, conducting heat poorly compared to metals. Heat from the core must slowly work its way through thousands of kilometers of rock to reach the surface and radiate into space. This takes an extraordinarily long time. The rate of cooling depends on mantle convection, hot rock rising, cooling, and sinking. But even this relatively rapid geological process operates over millions of years. Additionally, radioactive elements continue generating heat. While the most short-lived isotopes have decayed away, others with half-lives measured in billions of years still contribute significantly. Earth loses heat at a rate of about 44 trillion watts, which sounds like a lot, but spread across the entire planet and compared to the vast reservoir of thermal energy in the interior, it means cooling happens slowly. Computer models suggest Earth's core temperature has decreased by about 100 to 200 degrees Celsius per billion years. At this rate, the core will remain liquid and active for billions more years. Smaller planets like Mars cooled faster and largely lost their geological activity and magnetic fields within their first billion years. Earth's size has been a blessing, giving us a planet that remains dynamic, protective, and habitable. Could the core ever freeze? Here's a question about deep time. Eventually, yes, the core will solidify completely, but not for an extraordinarily long time. As Earth continues to radiate heat into space, the interior slowly cools. The inner core grows as more iron crystallizes from the liquid outer core, and the outer core shrinks. Eventually, given enough time, the entire outer core would crystallize into a solid mass. When would this happen? Estimates suggest it could take anywhere from 1 to several billion years for the outer core to completely solidify, though predictions are uncertain because we don't fully understand the cooling rate and how it might change. What would happen when the core freezes? The geodynamo would shut down. Without liquid metal churning in the outer core, Earth's magnetic field would disappear. The magnetosphere that protects us from solar wind would collapse. Over millions of years, the atmosphere would be stripped away by solar radiation, similar to what happened to Mars. Plate tectonics would likely cease as the mantle cooled and stiffened. eliminating the heat engine that drives continental drift. Volcanic activity would dwindle. Earth would become geologically dead, a cold rock orbiting the sun with no magnetic shield, no tectonic renewal, no volcanic outgassing to maintain an atmosphere. Life would face existential challenges. But this fate lies billions of years in the future, far beyond the lifespan of our species, or even our sun in its current form. For all of human timescales, and far beyond, Earth's core will remain hot, active, and protective. How fast is the core cooling? Think about the rate at which our planet loses its primordial heat. Scientists estimate that Earth's interior temperature decreases by roughly 50 to 100 degrees Celsius every billion years, though this rate isn't uniform and has likely varied throughout Earth's history. The cooling rate depends on several factors: how efficiently heat is transferred through the mantle, how much heat is still being generated by radioactive decay, and how the dynamics of mantle convection change over time. In the early Earth, when the planet was hotter and radioactive elements more abundant, cooling might have been faster. Now, as temperatures drop and long-lived radioactive isotopes slowly decline, the rate may be slowing. One way scientists track core cooling is by measuring the growth rate of the inner core. As the outer core cools, more iron crystallizes onto the inner core. Estimates suggest the inner core grows by about a millimeter per year, though this too varies. That might sound fast, but remember the inner core has been growing for perhaps a billion years or more, and it's still only about 1,220 kilometers in radius. At current rates, it would take roughly a billion more years to grow by another 1,000 kilometers. The cooling of Earth's core is a geological process, operating on timescales so vast that even millions of years make little difference. We live in a moment when the core is still robustly hot, actively convecting, generating a strong magnetic field, and powering the geological processes that shape our world. How old is the core? Let's go back to Earth's infancy. The core formed very early in our planet's history, probably within the first tens of millions of years after Earth began assembling from the solar nebula, about 4.54 billion years ago. How do we know? Several lines of evidence point to rapid core formation. First, the physics of planetary differentiation. When Earth was young and largely molten from the heat of formation, denser iron naturally sank toward the center, while lighter rocky material floated upward. This separation happened quickly, perhaps in just a few million years, once the planet was large and hot enough. Second, isotopic evidence from ancient rocks suggests the core was already formed by about 4.5 billion years ago. Certain elements partitioned differently between metal and rock, and their ratios in ancient rocks reflect core formation timing. Third, Earth's magnetic field appears in the geological record surprisingly early. Rocks as old as 3.5 to 4.2 billion years preserve magnetic signatures, indicating a functioning geodynamo, and therefore a liquid outer core already existed. The inner core is younger than the outer core. It began forming later, once the outer core cooled enough for iron to start crystallizing at the center. Estimates for when this began range from about 500 million to 2 billion years ago, though uncertainty is large. The inner core has been growing ever since, adding layer upon layer of crystallized iron as the planet gradually cools. The core is ancient, nearly as old as Earth itself, a survivor from the violent days of planetary formation. When did the inner core form? Here's a question that challenges our understanding of deep time. The inner core, that solid ball of iron at the planet's center, hasn't always existed. Early in Earth's history, the entire core was liquid. It was only when the planet cooled enough that iron began crystallizing at the very center, forming the solid inner core. But when did this happen? Scientists have proposed several methods to estimate the age of the inner core, but the answers vary widely. Some studies suggest it formed relatively recently, perhaps 500 to 700 million years ago. Others push the date back to around 1 to 1.5 billion years ago. while some estimates extend to 2 billion years or more. The uncertainty comes from the difficulty of the measurement. One approach looks at the strength of Earth's ancient magnetic field preserved in rocks. A jump in field strength around 1 to 1.5 billion years ago might indicate when the inner core started forming, because crystallization at the center would have enhanced the geodynamo. Another method examines how much heat the core is losing and works backward to calculate when crystallization would have begun. Despite the uncertainty, most scientists agree the inner core is younger than the outer core by billions of years, that it formed sometime in the last 1 to 2 billion years, and that it's still growing today as the planet continues its slow cooling. The inner core is a young feature by Earth standards, the newest addition to our planet's internal structure, yet it plays a crucial role in maintaining the magnetic field that protects us. How do scientists measure the core's age? Think about the challenge of dating something you can never see or sample directly. Scientists use indirect methods, piecing together clues from different lines of evidence. One key approach involves studying ancient magnetic fields preserved in rocks. When volcanic rocks cool, magnetic minerals within them align with Earth's magnetic field at that moment, locking in a record of the field's direction and strength. By studying rocks of different ages, scientists can reconstruct how Earth's magnetic field has changed over billions of years. A significant strengthening of the field in the past might indicate when the inner core formed, because the inner core's crystallization enhances the geodynamo. Another method uses thermal evolution models, computer simulations of how Earth has cooled over time. By inputting what we know about heat production from radioactive decay, heat loss through the mantle, and the energy released by core crystallization, these models can estimate when the inner core would have started forming. Seismic anisotropy, the directional variation in seismic wave speeds through the inner core, also provides clues. The pattern and strength of anisotropy might reflect how long the inner core has been growing and how its crystals have aligned over time. Each method has uncertainties and assumptions, which is why estimates vary. But by combining multiple approaches and refining our understanding of core physics, scientists are gradually narrowing down the age of the inner core, getting closer to understanding when this crucial component of Earth's engine room came into being. Till a rock rises, it cools, and eventually sinks back down, creating vast circulation patterns. This mantle convection drives plate tectonics, the moving of continents, the building of mountains, the creation of ocean basins. Heat that reaches the upper mantle and crust escapes through several mechanisms. Some heat flows steadily through rock by conduction, gradually warming the surface. But the most dramatic heat release happens at tectonic boundaries. At mid-ocean ridges, hot mantle rises close to the surface, partially melts, and creates new oceanic crust, releasing tremendous heat. At volcanic arcs and hotspots, magma erupts at the surface, carrying deep heat upward quickly. Even earthquakes release stored energy as heat. Ultimately, all this heat radiates from Earth's surface into space as infrared radiation, lost forever. The entire planet is slowly cooling, imperceptibly on human timescales, but measurably over billions of years. Heat from the core powers everything dynamic about our planet: volcanoes, earthquakes, mountain building, continental drift, even the magnetic field. Without it, Earth would be a dead world, geologically frozen and magnetically silent. How does the core affect volcanoes? Here's something to consider about the connection between the deepest and most surface parts of our planet. While volcanoes erupt on the surface, their energy ultimately traces back to the core's heat. The core heats the lower mantle, driving convection currents that rise through the mantle like slow-motion fountains. These rising currents, called mantle plumes, carry heat from the core mantle boundary upward over tens of millions of years. When a mantle plume reaches the upper mantle, it can partially melt, creating magma that rises toward the surface. Some of Earth's most dramatic volcanic features are thought to be fed by mantle plumes rooted near the core. Hawaii, Iceland, Yellowstone, these volcanic hotspots may sit above plumes that originate deep in the mantle, possibly even from the core mantle boundary. The core also affects volcanoes indirectly by powering plate tectonics. Heat escaping from the core drives mantle convection, which moves tectonic plates. Where plates collide, one plate often subducts beneath the other, descending into the mantle where it partially melts, creating magma that feeds volcanic arcs, like the Andes or the Pacific Ring of Fire. Where plates pull apart at mid-ocean ridges, hot mantle rises to fill the gap, melting and creating underwater volcanic chains. The entire cycle of volcanism, from subduction to spreading to hotspots, is powered by heat flowing from the core through the mantle. Without the core's heat, volcanoes would eventually cease as the planet cooled and convection stopped. How is the core linked to plate tectonics? Think about the engine that moves continents. Plate tectonics, the slow motion of Earth's surface broken into rigid plates, is driven fundamentally by heat escaping from the interior. And that heat originates in the core. The core is extraordinarily hot, hotter than the overlying mantle. Heat flows from hot to cold, so thermal energy moves from the core into the mantle. This heat causes the mantle to convect, with hot rock rising and cool rock sinking in vast circulation patterns. These convection currents exert forces on the overlying tectonic plates, dragging them along. But it's more complex than simple convection. The descending slabs of cold oceanic crust, subduction zones, are denser than the surrounding mantle and sink under their own weight, pulling the attached plate with them. This slab pull is a major driver of plate motion. Meanwhile, at mid-ocean ridges, mantle rises and partially melts, creating new oceanic crust that pushes plates apart. The entire system is powered by heat from below. Remove the core's heat, and mantle convection would weaken and eventually stop. Plates would cease moving. Subduction would end. Mountains would stop rising. Continents would no longer drift. Earth would become geologically dead, like Mars, which lost its internal heat and magnetic field billions of years ago, and now has no plate tectonics. The core's heat, flowing through the mantle, is what keeps our planet geologically alive, constantly reshaping the surface, creating new rock, recycling old material, and maintaining a dynamic environment. What drives Earth's geological activity? Let's consider the big picture of why Earth is such an active planet. Everything traces back to heat. Specifically, the heat stored in Earth's interior and how it escapes. The core is extraordinarily hot, containing both primordial heat from the planet's formation and heat from ongoing radioactive decay. This thermal energy must flow outward, and as it does, it powers all of Earth's geological processes. Heat from the core drives convection in the mantle, creating slow circulation currents of solid rock that flow like extremely thick honey. These currents move the tectonic plates floating on the asthenosphere, causing continents to drift, oceans to open and close, and mountains to rise. At plate boundaries, geological activity concentrates. Earthquakes occur, where plates grind past each other or collide. Volcanoes erupt, where plates separate, or where one plate descends beneath another. Mountains form, where continental plates crash together. All of this, the earthquakes, the volcanoes, the mountain building, the continental drift, is powered by heat flowing from the core through the mantle to the surface. Without this internal heat, Earth would be geologically dead. There would be no earthquakes, no volcanic eruptions, no new mountains forming. The surface would be static, ancient, heavily cratered, like the Moon or Mars. But Earth's size gave it enough internal heat to remain active for billions of years. The core acts as a thermal battery, slowly discharging its energy, and in doing so, it keeps the planet alive with geological activity that constantly renews the surface and maintains conditions favorable for life. How does the core power earthquakes? Here's the chain of connections, from the deepest earth to the ground shaking beneath your feet. The core's heat drives mantle convection, which moves tectonic plates. These plates are rigid slabs of lithosphere, crust and uppermost mantle, floating on the more pliable asthenosphere below. Where plates meet, they interact in three main ways. They pull apart at divergent boundaries. They collide at convergent boundaries, or they slide past each other at transform boundaries. These interactions create stress in the rocks. Over years or centuries, stress builds as plates push against each other, but friction prevents smooth motion. The rocks deform, storing elastic energy like a compressed spring. Eventually, the stress exceeds the strength of the rocks, and they suddenly slip, releasing the stored energy in seconds. This is an earthquake. The sudden motion sends seismic waves radiating outward through the earth, carrying the energy of the rupture. Without the core's heat-driving plate tectonics, there would be no tectonic stress. And without stress, there would be no earthquakes. Planets like Mars, which cooled and lost their internal heat engines, have no plate tectonics, and therefore no modern earthquakes. Earth's core, by keeping the planet geologically active, inadvertently powers the earthquakes that shake our world. It's a reminder that we live on a dynamic planet, one where the deep interior constantly influences the surface, where the stability we perceive is actually a balance of enormous forces driven by heat from thousands of kilometers below our feet. What are seismic waves? Think about what happens when you ring a bell. The metal vibrates, sending sound waves through the air. When an earthquake occurs, Earth rings like a bell, sending seismic waves through the planet's interior. These waves are vibrations traveling through rock, carrying the energy released by the earthquake. There are several types, each with different properties. Primary waves, or P waves, are compression waves that push and pull rock in the direction of travel, like sound waves moving through air. They're the fastest seismic waves, traveling at speeds up to 8 kilometers per second in the mantle and 11 kilometers per second in the core. P waves can travel through any material, solid or liquid. Secondary waves, or S waves, are shear waves that move rock perpendicular to the direction of travel, like shaking a rope. They're slower than P waves, and crucially, they can only travel through solids. When S waves encounter liquid, they stop. This property is how scientists discovered the liquid outer core. SEC waves disappear when they hit it, creating a shadow zone on the opposite side of the planet. There are also surface waves that travel along Earth's surface rather than through the interior, causing the most damage during earthquakes. By studying how these different waves travel, their speeds, paths, reflections, and refractions, seismologists can map Earth's interior structure in remarkable detail. Seismic waves are our primary tool for understanding the hidden layers beneath us, nature's gift for studying what we can never directly observe. How do seismic waves reveal Earth's secrets? Let's consider how scientists use earthquakes as natural experiments. When a large earthquake strikes anywhere on Earth, seismometers around the world detect the waves it generates. By comparing the arrival times and characteristics of waves at different stations, scientists can determine not just where the earthquake occurred, but also what those waves passed through on their journey. Waves traveling through denser material move faster. Waves encountering boundaries between different materials reflect or refract, changing direction. By analyzing thousands of earthquakes recorded over decades, scientists build detailed models of Earth's interior, like assembling a three-dimensional puzzle from countless pieces of data. For example, P waves traveling through the mantle arrive at seismometers more quickly than they would if traveling through uniform rock, revealing that the mantle's density and composition vary with depth. S waves completely disappear in the shadow zone opposite an earthquake, proving that part of the core is liquid. P waves that pass through the inner core travel at different speeds depending on their direction, revealing that the inner core has a crystalline structure with preferred orientation. Subtle variations in wave speeds reveal features at the core mantle boundary, blobs of unusually slow or fast material, topography on the boundary, regions of partial melting. Each earthquake provides new data, refining the models. Modern seismology uses sophisticated computer algorithms to process this data, creating increasingly detailed images of Earth's interior. It's detective work on a planetary scale, using vibrations to see the unseeable. How do scientists use earthquakes to see inside? Here's the process in more detail. Imagine Earth as a patient in a hospital, and earthquakes are the X-rays that reveal the patient's internal structure. Seismometers are the detectors, scattered across the globe in a network that records ground motion continuously. When an earthquake occurs, it generates seismic waves that spread out in all directions, traveling through the Earth. Some waves go deep, passing through the core. Others travel along more shallow paths through the mantle. Still others skim along the surface. Each path samples different parts of Earth's interior. By measuring when waves arrive at different stations, their travel times, scientists can calculate the path the waves took and how fast they traveled along that path. Faster travel indicates denser or more rigid material. Slower travel suggests less dense or partially molten rock. By analyzing waves from thousands of earthquakes, taking thousands of different paths through the planet, scientists create tomographic images, three-dimensional maps of seismic wave speeds throughout Earth's interior. These maps reveal structure in the mantle and core. They show cold subducting slabs descending into the mantle, hot mantle plumes rising toward the surface, variations in the core's properties. It's called seismic tomography, analogous to medical CT scans that use X-rays to image the body. Each earthquake adds more data, improving the resolution. Modern seismology uses massive computational resources to process this data, employing supercomputers to solve the mathematical problem of tracing wave paths through a complex three-dimensional Earth. The result is our best picture of what lies beneath our feet. What happens when waves bounce off the core? Think about seismic waves encountering the core mantle boundary, 2,900 kilometers below the surface. This boundary is one of the most dramatic contrasts in Earth's interior. Solid rock transitioning to liquid metal, a jump in density from about 5.5 to 10 grams per cubic centimeter, a boundary between silicate minerals and iron alloy. When P waves traveling down through the mantle hit this boundary, several things happen. Some of the wave energy reflects back upward, bouncing off the boundary like light reflecting from a mirror. Scientists can detect these reflected waves at seismometers, and by analyzing them, they learn about the properties of the boundary, its sharpness, its topography, its temperature. Most of the P-wave energy continues into the core, but the wave bends, refracts, as it enters the denser metal. Similar to how light bends when entering water, the wave also slows down slightly, traveling about 8 kilometers per second in the core, compared to 13 kilometers per second in the lower mantle. When S-waves hit the core mantle boundary, something dramatic happens. They stop. S-waves cannot travel through liquid, so they're blocked entirely by the liquid outer core. This creates a shadow zone on the opposite side of Earth, where no S-waves arrive, providing the original proof that the outer core is liquid. The way waves interact with the core mantle boundary reveals its nature, and by studying these interactions from countless earthquakes, scientists have mapped irregularities in the boundary and discovered that it's not smooth, but has complex structure. What is the core mantle boundary? Let's focus on this crucial frontier. The core mantle boundary, often abbreviated CMB, is the transition between Earth's rocky mantle and metallic core, located approximately 2,900 kilometers below the surface. It's one of the most important regions in Earth's interior, a place where heat transfer from the core to the mantle occurs, where the dynamics of both regions interact. The temperature jump across this boundary is extreme, roughly 1,000 degrees Celsius difference, from about 4,000 degrees at the bottom of the mantle to about 5,000 degrees at the top of the outer core. This thermal boundary layer is where hot core material meets cooler mantle material, driving convection in both regions. The CMB isn't perfectly smooth. Seismic studies reveal topographic variations, bumps and depressions, with relief possibly reaching tens of kilometers. Some of these features might be accumulations of dense material that sank through the mantle over billions of years, pooling at the bottom like sediment in a pond. Others might be thermal variations, regions where the boundary is particularly hot or cool. There are also large low shear velocity provinces, or LLSVPs, massive regions beneath Africa and the Pacific, where seismic waves travel unusually slowly. These blobs are thousands of kilometers across and hundreds of kilometers thick, possibly representing chemically distinct material or partially molten rock. The CMB is a dynamic region, coupling two of Earth's most important layers, facilitating heat transfer that powers plate tectonics and influencing the geodynamo that generates our magnetic field. It's a frontier we can study only indirectly, but one that plays an outsized role in Earth's behavior. What mysteries lie at that boundary? Here's where our knowledge becomes less certain and more intriguing. The core mantle boundary holds several unsolved mysteries. First, there are the large low shear velocity provinces, or LLSVPs, two enormous blobs of unusual material beneath Africa and the Pacific. Seismic waves slow down dramatically when passing through them, suggesting they're either hotter, compositionally different, or partially molten compared to surrounding mantle. But what exactly are they? Some scientists think they're piles of dense, iron-rich material that have accumulated over billions of years, possibly remnants from Earth's early differentiation. Others suggest they're superplumes, massive upwellings of hot mantle material, rooted at the CMB. Their origins, composition, and stability remain debated. Second, there are ultra-low velocity zones, or ULVZs, thin layers just above the CMB, where seismic waves slow down even more dramatically, sometimes by 30% or more. These zones are only a few kilometers to tens of kilometers thick, but are scattered around the CMB. They might be partial melt, rock that's partially molten at the base of the mantle, or they might be chemically distinct material. Third, the CMB shows variations in heat flow. Some regions transfer heat more efficiently than others, possibly due to temperature variations or differences in the mantle's lower boundary layer. These heat flow variations affect mantle convection patterns, influencing plate tectonics and volcanic activity at the surface. Understanding the CMB is crucial for understanding how Earth's interior works as a system, but direct observation is impossible, leaving many questions open. Are there mountains inside the Earth? Think about topography, the variations in elevation we see on Earth's surface, the mountains and valleys that shape landscapes. Now imagine similar features, but hidden deep inside the planet at the core mantle boundary. Seismic studies suggest the CMB isn't a smooth, uniform surface, but has topography, variations in elevation, where the boundary rises or falls by several kilometers. These internal mountains are nothing like surface mountains. They're not made of uplifted rock layers or volcanic piles, but rather variations in where the boundary between metal and rock sits. What causes this topography? Several factors might contribute. Chemical reactions at the boundary could create variations in density. Temperature variations could cause the boundary to bulge upward in hot spots or sink in cool regions. The large, low shear velocity provinces, those massive blobs beneath Africa and the Pacific, likely create topography where they sit on the CMB. Dense material accumulated there over billions of years would depress the boundary, creating valleys, while regions where hot core material rises might create bulges. Dynamic processes, the churning of mantle and core, constantly reshape this hidden topography. Unlike surface mountains that erode over millions of years, these internal features are shaped by thermal and chemical forces operating over geological time. They influence how heat flows from the core to the mantle, affecting mantle convection patterns and potentially influencing volcanic activity and plate tectonics at the surface. These hidden mountains, invisible to us, play roles in shaping the planet we see above. What are ultra-low velocity zones? Let's explore one of the strangest features at the core mantle boundary. Ultra-low velocity zones, or ULVZs, are thin layers where seismic waves slow down dramatically, sometimes by 20 to 30% or more compared to surrounding mantle rock. They're typically just a few kilometers to perhaps 40 kilometers thick, but they can extend laterally for tens or hundreds of kilometers. They're not everywhere at the CMB, but rather in patches, scattered around the boundary, in regions that don't follow an obvious pattern. What are these zones? Scientists have several hypotheses. One idea is that ULVZs are partial melt regions, where the intense heat from the core has partially melted the lowermost mantle rock. Molten material would slow seismic waves significantly. Another hypothesis is that ULVZs are chemically distinct material, perhaps iron-enriched rock that's denser and has different properties than normal mantle. A third possibility is that they're reaction zones, where core material and mantle material chemically interact, creating new compounds with unusual properties. Some scientists think ULVZs might be where mantle plumes originate, hot upwellings rooted at the CMB that rise through the mantle and feed volcanic hotspots like Hawaii. Others suggest they're remnants of subducted oceanic crust that descended all the way to the CMB and now sits there, partially molten. The truth is, we don't know for certain. ULVZs are incredibly difficult to study because they're so thin and far away, requiring the most precise seismic data to detect. Understanding them would tell us about heat flow at the CMB, about chemical interactions between core and mantle, and about the origins of mantle plumes, all crucial pieces of understanding how Earth's interior works. Could the core be uneven or lopsided? Here's something surprising. Recent research suggests the inner core might be asymmetric, with different properties in its eastern and western hemispheres. Seismic waves travel faster through the eastern hemisphere, roughly beneath Asia, than through the western hemisphere beneath the Americas and Atlantic. The difference is substantial enough to require explanation. What could cause this asymmetry? One hypothesis is that the inner core is growing faster on one side than the other. If crystallization is uneven, perhaps due to variations in the outer core's convection pattern, more iron might be crystallizing on one side, creating a younger, differently structured hemisphere. The crystals on the faster-growing side might then slide or flow toward the slower-growing side due to gravity, creating different crystal orientations in each hemisphere. Another possibility is that the asymmetry reflects how the inner core formed initially. If it didn't form uniformly from the center outward, but instead started growing asymmetrically, that original imbalance might persist. A third idea is that the outer core's convection pattern is asymmetric, influenced by irregularities at the core mantle boundary, or by the location of subducting slabs that cool the lower mantle unevenly. This asymmetric cooling could create asymmetric patterns in the outer core that affect how the inner core grows, or how its crystals align. Whatever the cause, the inner core's asymmetry suggests it's a more complex and dynamic structure than the simple uniform sphere we once imagined. It's still growing, still evolving, shaped by forces we're only beginning to understand. What is the blob deep beneath Africa? Think about one of Earth's most mysterious features. Beneath the continent of Africa, extending deep into the lower mantle and sitting on the core mantle boundary, lies an enormous region where seismic waves travel unusually slowly. It's part of one of the two large low shear velocity provinces, or LLSVPs, the other being beneath the Pacific Ocean. These aren't small features. Each is roughly the size of a continent and several hundred kilometers thick, containing about 2% of Earth's volume combined. The African blob, sometimes called the African superplume, has puzzled scientists since its discovery. Seismic waves slow down by a few percent when passing through it, suggesting it's either hotter than surrounding mantle, compositionally different, or both. But what is it? One leading theory is that it's a massive pile of dense iron-rich material that has accumulated at the base of the mantle over billions of years. This material might be primordial, remnants from Earth's early differentiation that never fully mixed with the rest of the mantle. Alternatively, it could be recycled oceanic crust that has descended via subduction, accumulated at the CMB, and now sits there too dense to be entrained in mantle convection. Another hypothesis is that it's simply extremely hot mantle, part of a massive upwelling or superplume. The blob might be the root of mantle plumes that feed volcanic hotspots at the surface. It appears stable over tens of millions of years, but might slowly evolve. Understanding this feature is crucial because it affects mantle convection, heat flow from the core, and possibly even the geodynamo and magnetic field. Could that blob be rising toward the surface? Let's consider whether these massive structures at the core mantle boundary might be ascending. If the blobs beneath Africa and the Pacific are hot mantle plumes or superplumes, they should be rising, driven by their buoyancy. Material that's hotter than its surroundings is less dense and wants to float upward. Some scientists believe these LLSVPs are indeed rising, slowly ascending through the mantle over tens of millions of years. As they rise, they might spawn smaller plumes that break off and rise faster, feeding volcanic hotspots at the surface. In fact, many of Earth's known hotspots, Hawaii, Reunion, Iceland, and others, seem to be clustered around the edges of these large structures, suggesting a connection. If the African blob is rising, it might one day cause dramatic volcanic activity across Africa, possibly even contributing to the continent's ongoing rifting in East Africa. However, other research suggests the blobs might be stationary, held in place at the CMB by their composition. If they're chemically distinct and denser than normal mantle, they might be stable piles that aren't rising at all. Instead, mantle convection might flow around them, like river water flowing around boulders. Hot material from the core mantle boundary might rise along the edges of these piles, creating plumes without the piles themselves moving. The truth remains uncertain. Studying the dynamics of these deep structures is extraordinarily difficult, requiring computer models that push the limits of current computing power and observations that test the resolution of seismic networks. Whether rising or stationary, these blobs play crucial roles in Earth's internal dynamics. What is a mantle plume? Here's a concept that helps explain some of Earth's most dramatic volcanic features. A mantle plume is a column of hot rock rising from deep in the mantle, perhaps from the core mantle boundary, toward the surface. Think of it like a lava lamp, where heated wax becomes buoyant and rises in a column. In Earth's mantle, rock that's heated at the CMB becomes less dense than surrounding rock and begins to rise. As it rises, it maintains its heat better than the surrounding mantle cools, so it continues ascending as a coherent column or mushroom-shaped structure. The rising rock partially melts as it approaches the surface, and pressure decreases, creating magma. This magma can erupt at the surface, creating volcanic activity. Unlike the volcanism at plate boundaries, which is caused by plate tectonics, hotspot volcanism from mantle plumes occurs in the middle of tectonic plates. Hawaii is the classic example, a volcanic island chain in the middle of the Pacific plate, far from any plate boundary, fed by a mantle plume that has been active for tens of millions of years. As the Pacific plate moves over the stationary plume, it creates a chain of volcanoes, with older ones to the northwest and younger ones to the southeast. Other proposed plume locations include Yellowstone, Iceland, Reunion, and several others. Not all scientists agree on which volcanic features are caused by plumes versus other mechanisms, and the debate continues. But the plume hypothesis remains the leading explanation for volcanic hotspots that can't be explained by plate tectonics alone. If plumes originate at the CMB, they provide a direct connection between the core's heat and surface volcanism, a pathway for deep heat to reach the surface relatively quickly. How do mantle plumes create volcanoes? Think about the journey of a mantle plume from the core mantle boundary to the surface. It begins as hot rock, heated by the core, perhaps 200 to 300 degrees hotter than surrounding mantle. This temperature difference makes it buoyant, and it begins to rise. The ascent is slow by human standards, perhaps a few centimeters per year, but fast by geological standards. As the plume rises, it maintains its heat because hot rock is a poor conductor, and the column's interior stays hot even as its edges cool and slow down. The rising plume creates a mushroom-shaped head, followed by a narrower tail. When the plume head reaches the upper mantle, perhaps 100 to 200 kilometers below the surface, pressure has decreased enough that the hot rock begins to partially melt. Rock melting temperature depends on pressure. Lower pressure means lower melting point. The plume doesn't melt entirely, but perhaps 10 to 30% becomes liquid magma, while the rest remains solid but extremely hot. This magma is buoyant and rises further, working its way through cracks and weak zones in the overlying rock. If it reaches the surface, it erupts, creating volcanic activity. The eruptions from hotspots are typically basaltic, relatively fluid lava that flows freely, building shield volcanoes like those in Hawaii. Over time, as a tectonic plate moves over the stationary plume, a chain of volcanoes forms, recording the plate's motion. The Hawaiian Islands stretch over 3,000 kilometers from the currently active volcanoes on the Big Island to the eroded remnants of ancient volcanoes in the northwest, all created by the same mantle plume over 80 million years. What is the role of the core in supervolcanoes? Let's consider whether the core plays a role in Earth's most catastrophic volcanic eruptions. Supervolcanoes, volcanic systems capable of erupting more than 1,000 cubic kilometers of material in a single event, are among the most powerful geological phenomena on Earth. Yellowstone, Toba, Topo. These systems have produced eruptions that covered continents in ash and likely affected global climate for years. What causes supervolcanoes? The leading hypothesis involves mantle plumes, a plume rising from deep in the mantle, possibly from the core mantle boundary, brings enormous amounts of heat toward the surface. If this heat accumulates beneath the crust faster than it can escape, magma builds up in a massive underground chamber. Over hundreds of thousands of years, this chamber grows, filling with molten and partially molten rock. Eventually, the pressure becomes too great, the overlying rock fractures, and the magma erupts catastrophically. So the core's role is indirect, but crucial. It provides the heat that drives the mantle plume, which in turn creates the conditions for supervolcanic eruptions. Without heat from the core, mantle plumes wouldn't exist, and supervolcanoes wouldn't form. It's another reminder that Earth's surface and interior are intimately connected, that events thousands of kilometers deep can eventually manifest as dramatic surface changes. The timescales are vast. A mantle plume might take tens of millions of years to rise from the CMB to the surface, but the consequences can be planet-altering. The core's heat, slowly but inexorably flowing outward, occasionally finds pathways to the surface that release energy in concentrated, violent bursts. Could the core cause a mass extinction? Here's a sobering thought to contemplate. Could changes in the core's behavior contribute to mass extinction events? The connection isn't direct, but there are hypothetical pathways. One involves the magnetic field. If the geodynamo in the outer core weakens significantly or shut down temporarily, Earth's magnetic shield would weaken or disappear. This would expose the surface to increased cosmic radiation and solar particles. The ozone layer might be damaged, allowing more harmful ultraviolet radiation to reach the surface, stressing ecosystems. However, the geological record shows that magnetic field reversals, when the field weakens during the transition between polarities, haven't consistently correlated with mass extinctions, suggesting this mechanism alone isn't sufficient. Another potential pathway involves massive volcanic eruptions. If changes in core heat output affected mantle plume activity, it could trigger large igneous provinces, enormous volcanic eruptions that pour out hundreds of thousands of cubic kilometers of lava over millions of years. These eruptions release massive amounts of greenhouse gases, potentially causing rapid climate change, ocean acidification, and ecological collapse. Several mass extinctions, including the Permian-Triassic extinction 252 million years ago, coincide with large igneous provinces. The connection between core dynamics and these eruptions remains speculative, but if core heat flow varies over tens of millions of years, it could affect mantle convection patterns and plume activity. The core doesn't directly cause extinctions, but its influence on magnetic fields, volcanic activity, and plate tectonics means it shapes the planet's habitability over geological time. What happens when the core changes speed? Think about the inner core's rotation relative to the rest of the planet. Recent research suggests the inner core's rotation rate isn't constant, but varies over decades, sometimes rotating slightly faster than the surface, sometimes slower in an oscillating pattern. When the inner core changes speed, what happens? First, it affects the magnetic field. The inner core and outer core are coupled through magnetic forces, and changes in the inner core's motion influence convection patterns in the liquid outer core. This can alter the strength and structure of the magnetic field, contributing to secular variation, the slow changes in the field that scientists carefully track. Second, conservation of angular momentum means that if the inner core speeds up or slows down, something else must compensate. The outer core, mantle, or even Earth's rotation could be affected, though the effects are tiny. Some scientists have proposed correlations between inner core rotation changes and small variations in the length of day, though the evidence remains debated. Third, the core mantle boundary might experience changes in stress and heat flow if core dynamics shift. These could theoretically affect mantle convection and, over very long timescales, influence plate tectonics or volcanic activity, though any such effects would be subtle and difficult to detect. The inner core's rotation changes are fascinating because they reveal that the core is dynamic, constantly adjusting to changing conditions in the outer core and mantle, part of a coupled system where each component influences the others. Understanding these changes helps scientists develop better models of how Earth's interior works as an integrated whole. Is the inner core spinning faster than the Earth? Let's revisit this question with recent findings in mind. For years, scientists believed the inner core rotated slightly faster than the rest of the planet, completing an extra rotation relative to the surface every few hundred years. This superrotation was detected by comparing seismic waves from earthquakes in the same location recorded decades apart. The travel times changed subtly, consistent with the inner core's anisotropy, its directional variation in seismic wave speeds, rotating relative to the seismometers. However, research published in 2023 has complicated this picture dramatically. Some studies now suggest the inner core's superrotation paused around 2009 and may have since reversed, with the inner core now rotating slightly slower than the surface. Other research proposes that the inner core's rotation oscillates over a 70-year cycle, alternately leading and lagging the surface rotation. Yet other scientists question whether the changes being detected are rotation at all, or might reflect changes in the structure of the inner core itself. The debate continues because the observations are extremely difficult. They require precise measurements of tiny changes in seismic wave travel times over decades, and different research groups use different earthquakes and analysis methods, sometimes reaching different conclusions. What's clear is that the inner core doesn't rotate rigidly with the rest of the planet, that its motion relative to the surface is complex and variable, and that understanding this motion requires continued observations and improved models of core dynamics. What if the core stops rotating? Here's a question that requires careful clarification. The core won't stop rotating in an absolute sense. It's gravitationally coupled to the rest of the planet and rotates once per day, along with everything else. But what if the geodynamo stopped? What if convection in the outer core ceased and the magnetic field disappeared. This is theoretically possible if the core cooled enough that thermal and compositional buoyancy could no longer drive convection. What would happen? Most critically, Earth's magnetic field would collapse. The magnetosphere that shields us from solar wind and cosmic radiation would vanish. Over thousands to millions of years, the solar wind would begin stripping away Earth's atmosphere, particularly lighter elements like hydrogen. This is what happened to Mars when its core cooled and its magnetic field disappeared billions of years ago. Without a magnetic field, the surface would be exposed to increased radiation. The ozone layer would likely be damaged or destroyed, allowing harmful ultraviolet radiation to reach the surface. Life would face severe stress. Technology would be vulnerable to solar storms without the magnetosphere's protection. Auroras would disappear. Migratory animals that use magnetic fields for navigation would be disoriented. In the very long term, millions of years, Earth could become more like Mars, cold, dry, with a thin atmosphere, inhospitable to life. However, this scenario is extremely unlikely on human timescales. The core will remain hot and convecting for billions of years more. Even if the field weakens significantly, it would likely recover, as it has after previous reversals. The core stopping is a threat only on geological timescales far in the future. What happens to heat inside the Earth? Let's trace the journey of heat from the core to the surface. Deep inside, the core generates heat through radioactive decay and retains primordial heat from Earth's formation. This heat must go somewhere. It can't be created or destroyed, only moved. Heat flows from hot to cold, so it moves from the scorching core through the cooler mantle toward the even cooler crust and surface. In the outer core, heat transfer happens through convection. Hot liquid iron rises, cools slightly, and denser iron sinks. This churning motion not only moves heat, but also generates the magnetic field. At the core mantle boundary, heat transfers from the core into the lower mantle. This boundary layer is crucial. Heat escaping from the core drives convection in the mantle. Hot mantle rock rises slowly toward the surface, traveling perhaps a few centimeters per year, taking millions of years to complete a convection cycle. As